You type a question into an AI, hit enter, and boom, a response starts streaming back almost instantly. It really does feel like magic, doesn't it? But it's not. What's really happening is an incredibly complex, high-speed journey. So today, we're going to follow the life of a single prompt and uncover the brilliant engineering that makes it all possible.
So, let's get right into it. The second you send your prompt, you kick off this hidden two-stage race inside the machine. It's a process filled with massive challenges, serious bottlenecks, and some truly ingenious solutions. We're going to pop the hood on that black box and trace the exact path your words take.
All right, the journey begins. Before an AI can even begin to understand your prompt, it has to be translated. And here's the first thing you have to get. The AI doesn't speak English, or Spanish, or any human language for that matter. Its entire world is just pure numbers. So the very first step is a complete transformation.
This process starts with something called tokenization. As you can see here, your simple sentence, "Hi, my name is," gets chopped up and converted into a series of numbers, or token IDs. From this point on, the AI is only dealing with these numbers, not your words. Then these IDs get in line, entering a waiting queue before they're allowed into the main event, the inference engine.
Once it's inside, your prompt faces this two-part process: prefill and decode. Now, these aren't just two simple steps. They are fundamentally different kinds of work, and each one places its own unique demands on the system.
Okay, so this is absolutely crucial. The prefill stage is the heavy lift. This is where the AI reads all of your prompt's tokens at once and does a massive calculation to understand the context. You could think of it as the AI creating a short-term memory of your request. Then the decode stage kicks in. This is the super fast part you actually see. It reuses that initial memory over and over again to predict just one new word at a time, streaming them to your screen.
And that short-term memory I just mentioned, well, that's the secret sauce to this whole operation. It has a very specific name, and honestly, understanding this one concept is the key to understanding how AI can be so fast.
It's called the key value cache, or just KV cache for short. See, every time the AI generates a new word, it needs to look at all the previous words for context. Instead of rereading and recalculating the entire conversation from scratch every single time, it smartly stores the most important computational results right here, in this cache. It's a brilliant way to avoid doing the same work over and over, and it's what makes that decode stage so incredibly quick. But here's the twist. Here's the central conflict in our prompt's journey. This KV cache, while being totally essential for speed, is an absolute memory hog. It takes up an enormous amount of GPU VRAM, which is, by far, the most expensive and limited resource in the entire system.
In this chart, wow, it really puts it into perspective. Just look at that. The KV cache can eat up around 80% of the GPU's entire memory. The actual AI model itself, the weights, is just a tiny fraction of that. This means the single biggest challenge in AI inference isn't the raw calculation, but just efficiently managing this gigantic chunk of cache memory.
So how in the world do you solve such a massive memory problem? Well, engineers borrowed a brilliant idea that's been used in computer operating systems for decades and adapted it for AI, and it's called page detention.
This is the perfect way to think about it. If GPU memory is prime, expensive real estate, you can't afford to have any empty, unused lots just sitting there. Page detention is like the hyper-efficient property manager that makes sure every single square inch of that valuable land is being used with absolutely zero waste.
So here's how it works. Instead of needing one giant, continuous piece of memory, page detention breaks the KV cache into small, fixed-size blocks. A prompt's data can then be scattered across any of these free blocks, wherever they might be. They don't even have to be next to each other. And to keep track of it all, a page table on the CPU acts like a map, telling the GPU exactly where to find all the pieces for any specific prompt. It's a really clever system.
And this is the beautiful result. The moment a prompt is finished and its memory isn't needed anymore, those blocks are instantly marked as free on the map. They can then be immediately assigned to a brand new prompt that's coming in. This system pretty much eliminates memory waste entirely.
And this incredible efficiency in memory management, well, it unlocks another huge performance boost. With page detention handling the memory so well, the system can process lots of user requests in a much smarter way, using something called continuous batching. See, in the old way, with static batching, you'd process a group of prompts, but the entire group had to wait for the very slowest one to finish before the next batch could even start. This led to tons of wasted GPU time. But with continuous batching, the moment one prompt finishes, its resources are freed up and a new prompt from the waiting queue can jump in immediately. There's no waiting, there's no waste. The GPU is kept busy all the time.
Okay, we've gone pretty deep into the technical stuff. Tokenization, KV cache, page detention. But what does all this complex, behind-the-scenes engineering actually mean for you, the person just trying to get an answer to a question?
Simply put, it's everything. This relentless focus on efficiency is exactly what makes large-scale AI services possible and affordable in the first place. It's why thousands of people can be on the same system at once without it just grinding to a halt. It's the reason your answer appears so quickly, and it's what directly drives down the cost of every single word the AI generates.
So the life of a prompt is this incredible journey of transformation and optimization. From page detention to continuous batching, these are the kinds of innovations that are powering the AI you use every single day. And that leaves us with a pretty exciting question. As these models get even bigger and more powerful, what comes next? What new breakthroughs will we need to invent to manage all that complexity and keep things moving at the speed of thought?